You have been brazenly deceived. Open any history of technology textbook, and you will read that the refrigerator appeared in the 20th century. And before that, humanity lived in the Dark Ages and stored food in damp pits. But this official version falls apart as soon as you examine the real figures. How can we explain that 2,500 years before the invention of the electrical socket, industrial amounts of ice were produced in the scorching Persian desert? How is it that in the 19th century, ships transported frozen water across the equator with accuracy of losses down to 1%, while one company consumed 500,000 tons of ice per year? Why are we told about primitive cellars when it came to a global infrastructure that operated without a single gram of fuel? And the main question is, what price did we pay to forget this technology? Imagine, you open a textbook on the history of technology. There's a page dedicated to the refrigerator. It says something like, in 1913, the first domestic refrigerator was introduced. This changed people's lives forever. And that's it. Period. The next section is about the telephone. A beautiful story. Short. Convenient. But here's the question. If cold management is an achievement of the 20th century, how do you explain that as far back as 1833, a ship left Boston carrying a cargo of ice and arrived in Calcutta 4 months later through the tropics, bringing back more than half of the cargo intact? How do you explain that in the 1880s, a Chicago company consumed nearly 500,000 tons of natural ice a year? How do you explain that in the center of the Iranian desert, where summer temperatures reach 40 degrees Celsius, there are clay conical towers over 2,000 years old that produced ice without a single gram of fuel? These are not random facts. They are fragments of a single system. A system that is hardly ever articulated as a whole in the popular narrative of technology. And before we go any further, one important point. We are now going to examine 4 objects, 4 points on the map and on the timeline. I'm not asking you to believe what I say. I'm asking you to check it for yourself. All the numbers, all the dates, all the technical details are real and documented. I will address objections as we go along. By the end, you should be left with not a conclusion, but a question. One specific question that is difficult to dismiss with a simple explanation. Let's begin with Persia. 400 years before our era. The Dasht-i-Lut Desert, one of the hottest places on the planet. In the summer, surface temperatures here have been recorded at nearly 70 degrees. And in this desert, Persian engineers constructed structures that produced and stored ice. They didn't bring it in, they produced it right on site. Open a photograph of a yachtchala, that's what this structure is called. You will see a conical dome rising up to 18 meters, made of fired clay. At first glance, it looks something like a barn or a warehouse. But when you start to break down the construction into parts, the official description of traditional ice house begins to fall apart at the seams. Look, on the northern side of the dome stands a wall. Its height reaches up to 10 meters, and its length extends to 50. It is oriented strictly along the east-west axis. This is not an incidental construction. The wall creates a constant shadow on the northern side, where water from underground aqueducts accumulates in shallow channels. During the day, temperatures soar to +40. At night, the sky over the desert is absolutely clear. The cooled air releases the heat accumulated throughout the day directly into outer space through radiative cooling. Water in the shade freezes. This phenomenon is known as radiative cooling. And this is not a folk trick. It is the precise calculation of a physical phenomenon. Now, the dome itself. It is built from a material that is virtually absent in Western construction tradition. It is called sarud. Its composition includes sand, clay, lime, ash, goat hair, and egg white in precisely measured proportions. This results in a mixture with two unique properties: absolute waterproofness and extremely low thermal conductivity. This means that ice inside does not melt from the humidity outside, nor does it melt from the heat outside. The most obvious explanation? Well, it's just an old cellar, something that was built everywhere. Okay, then answer one question. A regular cellar is a pit in the ground covered by a roof. Why is there a conical dome with an opening at the top here? Because this is not just a roof. It's a ventilation system. Warm air rises and exits through the top. Cold air descends into the underground chamber. The volume of this chamber is up to 5,000 cubic meters. This is not a cellar. This is a thermodynamic device. And here's what's important. Ice from the Yachtchal was obtained not only at the Shah's court. In Isfahan and Yazd, ice was sold on the streets for cooling drinks and making sherbets. The poorest layers of the population. Public urban infrastructure. 200 years before Carlo Gotti sold the first penny ice cream in London. Building such structures does not simply mean mixing clay with egg whites. It is an architectural school with specialized craftsmen who passed down the precise proportions of the mixture through generations. It involves organized water extraction from underground aqueducts. It reflects an understanding of radiative physics expressed not in formulas, but in the shape of the building. Call it what you want. Just don't call it folk ingenuity. Now for something important. Try to reproduce this system on your own. Take any construction reference book and search for the composition of saruj. Finding it is not easy. This material is extremely rare in modern engineering catalogs. Its recipe has mainly reached us through the descriptions of researchers who collected samples from real existing yachtchals and analyzed their composition. And here's what's strange. Over 2,000 years, construction science has mastered concrete, plastic, and polyurethane insulation. Yet this mixture has never become part of the standard engineering canon. Another detail that is usually not mentioned. The system of channels that supplied water to the yachtchals was called carrés, subterranean aqueducts carved into the rock, sometimes at depths of up to 30 meters. The construction of a single carrés required decades of work by specialized crews. This was not about rural handicrafts. It was a matter of state infrastructure that was designed, built, and maintained as a unified system. The yachtchal was not an independent entity. It was the endpoint of a water thermal infrastructure that spanned entire provinces. There are only a few hundred surviving yachtchals in Iran. This is not a unique experiment by a clever architect. It is standard urban infrastructure, like plumbing or sewage. Things that we also consider modern achievements, even though Rome had them 2,000 years ago. And now let's fast forward 1,200 years. The year is 1833, Boston. A man named Frederick Tudor is loading 180 tons of ice onto the ship Tuscany. The destination of the cargo is Calcutta. The distance is about 16,000 miles across the Atlantic, around the Cape of Good Hope, and through the Indian Ocean. 4 months of travel through tropical waters. Many will now say, the ice will melt in a week. Fine. Then explain why 100 tons of unmelted ice were unloaded from the hold in the port of Calcutta. The losses amounted to 44%. Indeed, 44. And this is not a catastrophe. It is a calculated norm. This means that the packing method, sawdust on the outside, rice husk between the blocks, yielded predictable, reproducible results. When losses become a calculated norm, it is called an industrial standard, not an experiment, not a fluke. But Tudor didn't just send a ship. He built infrastructure at the other end of the route. In 35, a glacier in Calcutta. In 41, in Madras. In 43, in Bombay. These were special double-walled brick buildings insulated with sawdust, specifically designed for tropical humidity. Not temporary warehouses, architectural structures that operated for decades. Look at what happened next. Ice in colonial India became more than just a commodity. It became a line of division. Hospitals in the White City used it to cool feverish patients, at a time when there were simply no other ways to lower critical temperatures. Outside this zone, the Black City, there was no access to the system. Ice literally became a tool of the colonial structure. Not a luxury, a tool. This is not a metaphor. It is a construction project. The Tudor infrastructure demonstrated that cold can be transported across half the planet if the problem of insulation is solved. The problem was solved. And at that moment, the next question arises. Okay, ice has been brought to London. But how do we deliver it from the dock to the consumer? Who built the last mile of the cold chain? But first, one technical detail that often goes unnoticed. Sawdust. It was sawdust that became the key insulating material for the ocean transport of ice. Why sawdust? Because it contains millions of microscopic air pockets. Air is a poor conductor of heat. That is insulation. Sawdust was a cheap byproduct of the woodworking industry, and there was plenty of it in Boston, near the ice harvesting bases on the frozen lakes of New England. No one invented this material specifically. It was just used correctly, in the right volumes and with the right density of packing. And now, here's what's interesting. Tudor didn't just send out the first ship and wait for results. He spent several years experimenting before achieving reproducible outcomes. The first voyages ended with significant losses. He altered the thickness of the sawdust layer, changed the density of the block arrangements, and modified the design of the hold. These were years of applied research in real market conditions. By 1833, the year of the voyage to Calcutta, the technology had been refined. 44% losses are not the result of a first attempt. They are the outcome of a decade-long iterative process. What is it called? It is called R&D, research and development. Just without universities, without government funding, and without a patent office. And here's another detail worth noting. The building that Tudor constructed in Madras in 1841 still stands today. It is now called Vivekananda Ilam and is a monument of architecture. But when you read about this building in tourist guides or on official websites, what does it say? It talks about its current function, about what is there now, about its colonial architecture. Regarding ice, at best there's a single line in the history section. a building specifically designed to combat tropical humidity for ice storage, a task that European construction tradition was practically unfamiliar with, is described simply as an ancient building in the style of colonial neoclassicism. Engineering has vanished. Only aesthetics remain. Now consider another question. Tudor built ice houses in the three largest ports of British India: Calcutta, Madras, and Bombay. All three are in the tropics. All three are specialized double-walled structures with sawdust insulation. This is a three-point network of specialized cold infrastructure on the subcontinent. Not a single object, a system. Constructing these buildings required an understanding of the local climate, agreements with the colonial administration, supply of insulation materials, and training of local personnel for maintenance. This is not a one-off deal. It is an infrastructure project. When we say the Boston merchant traded in ice, we are greatly oversimplifying. It would be more accurate to say the American entrepreneur established a transoceanic cold chain with infrastructure hubs at both ends of the route. This represents a different scale of description, and it aligns much more closely with reality. King's Cross, London, the 1850s. Under a warehouse in the Battle Bridge Basin, the Swiss entrepreneur Carlo Gotti is building two brick wells. The diameter of each is about 9 meters. The depth exceeds 12. From the outside, it appears to be an ordinary warehouse by the canal. Inside, it's an industrial logistics hub. The supply chain operated like this. Ice was cut from the frozen lakes of Norway, loaded onto ships, and delivered to the London docks. There, it was transferred to horse-drawn barges and transported through the canal directly into the warehouse. The blocks were packed into wells so tightly that by the time they reached the consumer, roughly 25% of their mass was lost from the Norwegian lake to the London kitchen. 1 to 4. On the journey through the North Sea, through the docks and the city canals, I initially thought, well, this is a wealthy merchant. He had a small ice cream shop. Until I stumbled upon the number. Gotti sold up to 10,000 portions of ice cream a day, at 1 penny each. Before him, ice in London was a privilege of the aristocracy. Afterward, it became a street commodity. This is not just a business story. Think about the mechanism. Industrial-scale storage allowed the price to drop to 1 penny. 1 penny was the price of a pint of beer for a worker. Cold became accessible to everyone. Not because a new production technology emerged, but because someone built a large enough basement. A network of yellow-brown vans delivered ice throughout the capital. Each van had its own route, schedule, and regular clients. The term just-in-time supply chain would be coined about 100 years later in the Japanese automotive industry. But the mechanism was the same. Gotti simply implemented it earlier. Remember this figure, 25% losses. It's almost the same as Tudor's on the route through the tropical ocean. 2 different continents, 2 different routes, 2 different climates, and the same accuracy in managing losses. This is not a coincidence. It is a sign of a well-honed technology. Now, one question that I ask you to keep in mind until the end of this video. The Gotti warehouses in King's Cross today are the London Museum of Canals, a tourist attraction. They hold tours, sell tickets, and tell the history of London's waterways. Ice is mentioned as a curious fact. Look, they stored ice here in the 19th century. Isn't that amusing? An industrial logistics hub that once supplied a 1 million-person city with essentials has become a museum curiosity. When exactly did ice stop being a staple product and turn into a curious fact? When the electric refrigerator was invented, and that was the end of the story. Let's return to the numbers. Gotti sold ice cream for pennies. This is the most well-known fact about him. But there's another one. His ice supplied London hospitals, fish markets, butcher shops, breweries where ice was used to control fermentation, restaurants, pastry shops, and hotels. It wasn't just one industry. It was urban infrastructure without which the normal functioning of a metropolis would have been simply impossible. No less critical than plumbing or sewage systems. It's just not talked about. Now, one point that deserves separate contemplation. Gotti brought ice from Norway, not from Scotland, not from the Alps. From Norway, across the North Sea. Why so far? Because Norwegian ice was purer. Mountain lakes provided clear, dense, slowly melting ice, free of impurities. By that time, London's waters were so polluted with industrial waste that their ice was unsuitable for use in food production and medicine. In other words, Gotti transported ice over 500 miles of sea route, not because he had no other options, but because the quality of the product mattered. He had quality standards for an ice dealer in the 19th century. Now comes the most uncomfortable part. Chicago, the 1880s. The Packingtown District. Here, the largest meat processing companies in the world operate. Armour, Swift, Morris. Cattle were driven here from the Great Plains, slaughtered here, and from here the meat was sent to the East Coast. Thousands of tons daily. The Swift Company alone consumed nearly 500,000 tons of natural ice per year. 500,000 tons. The entire export and import of ice through London in peak years amounted to about 50,000 tons, 10 times less, from just one company. It is officially believed that industrial cold logistics emerged with ammonia compressors in the early 20th century. Okay, so how did Swift's system operate 30 years before that? Before the invention of the refrigerated car, meat was transported using live livestock. The animals lost weight on the journey, resulting in a direct financial loss. Every kilogram burned by the animal on the road represented money lost that no one received. Gustavus Swift approached the problem differently. He designed a car with ice bunkers at both ends. Cold air circulated around the carcasses naturally due to the temperature difference. The meat was transported already as dressed carcasses, and it arrived intact. But that's only half of the engineering. The ice in the car is melting. This means a network of stations along the railroad is needed, where the cars can replenish their supplies. Swift built it. The ice for this network was gathered on the Fox River and stored in connected ice houses, each 30 by 30 meters, 6 meters tall. The system operated like a conveyor belt. Collection in winter, storage in the ice houses, delivery to the stations, loading into the cars, and transportation of meat to New York and Boston. Think about what this means in practice. Before this system, beef was a seasonal local product. Afterward, it became a year-round global commodity. Not because someone invented a new way to slaughter cattle, but because someone established a cold chain spanning thousands of miles using natural ice. At this point, the standard objection arises. Well, it was still a primitive technology, and it broke down when regular refrigerators came along. Fair enough. Let's do the math. 500,000 tons of ice per year. This means that in the summer, millions of tons of ice, harvested in winter, are stored in thousands of ice houses across the Midwest. The logistics of delivery operate seamlessly in the conditions of an American summer. Meat arrives in New York in pristine condition every day. Is this primitive technology? Or is it a complex infrastructure that was simply replaced by another complex infrastructure, and the first was conveniently forgotten? Let's look at the numbers one more time. The ice houses in Yorkville and Oswego, where the ice for the SWIFT system was stored, are 30 by 30 meters, with a height of 6 meters. One such ice house contains 2,700 cubic meters of ice. But there wasn't just one or two. There were several dozen along the supply routes. Each needed to be filled in the winter, monitored for ice conditions throughout the summer, and managed for logistics in transporting to the stations. This required hundreds of specialized workers, process engineers, managers, and transport operators. In this context, the standard argument goes, but it all depended on the winter anyway. No winter, no ice. True. Now consider this. The ammonia plants producing artificial ice in the early 20th century relied on a continuous supply of ammonia, coal for steam generators, spare parts for compressors, and skilled mechanics for maintenance. Each of these dependencies is a point of failure. There were just as many as in a natural system, just different ones. The difference lies in the fact that the natural system was visible and understandable. Here is a river, here is winter, here is ice, here is a glacier. The new system has hidden its dependencies within the machine, and we have stopped thinking about them. Whether it is right to call this progress or merely a replacement is an open question. But here is an undeniable fact. When, in 1885, Swift's refrigerated cars first began transporting meat en masse from Chicago to the East Coast, the butchers of New York declared a boycott and demanded a ban on that trash. They understood what was happening. Not because the meat was bad, but because their entire business model, buying and slaughtering live cattle right in New York, was becoming obsolete. They lost, because Swift's cold chain was cheaper, more accurate, and more scalable than any local alternative. Cold has triumphed over locality. This is perhaps the main thing that this system has provided. And here's another point that is rarely mentioned. By 1890, the meat industry in Argentina, Australia, and New Zealand began supplying chilled meat to Europe across the Atlantic via refrigerated steamships. This became possible because by that time there was already a developed logistics system, storage standards, distribution networks, and consumers accustomed to chilled products. All of this was made possible by the American natural ice system. The mechanical refrigerator appeared in a world where cold logistics was the norm, not a novelty. It did not start from scratch. Now stop and look at these four objects together. The Persian Desert, 400 years before our era. A passive thermodynamic apparatus that produces and stores ice for the urban population without a single gram of fuel. A Boston merchant, 1833. Transoceanic ice logistics, with calculated loss rates and specialized architecture at the other end of the route. A London entrepreneur, the 1850s. Industrial underground wells and an urban distribution network that transformed ice from an aristocratic privilege into a penny commodity. A Chicago corporation, the 1880s. 500,000 tons a year, refrigerated cars, a network of ice refueling stations, a global meat market. These are not four separate cases. They are 4 links in a chain. Each subsequent link builds upon what the previous one has resolved. The Persians solved the problem of material and form, how to store ice in heat. Tudor addressed the transportation problem, how to deliver ice across the ocean. Gotti tackled the issue of urban logistics, how to get ice to the final consumer. Swift resolved the problem of industrial scale, how to establish a cold chain across thousands of miles. Look, each of these individuals built upon the knowledge of the previous level. Tudor didn't invent insulation. He improved what already existed. Gotti didn't come up with underground glaciers. He scaled them. Swift didn't create the refrigeration principle. He integrated it into an industrial conveyor. This appears to be a sequential solution to the same engineering problem at different levels of scale, from the desert to a transcontinental conveyor. And now, a technical question that usually goes unasked. Where did the ice for the lakes of New England, from which Tudor gathered it, actually come from? In winter, the lakes freeze, yes, but the ice had to be cut in the right place, with the right thickness and quality. Clear ice without bubbles, the kind that forms from the bottom, lasted longer than murky surface ice. Ice cutters knew this and chose their locations accordingly. It was a profession, with varying qualifications, different rates of pay, and accumulated experience that was passed down from father to son. 1885. In the United States, there were about 8,000 enterprises focused on harvesting natural ice. 8,000. Tens of thousands of workers. Hundreds of thousands of tons of finished product. A network of storages from Maine to Florida. It was a fully fledged industry with investments, competition, technological innovations, and professional standards. In 20 years, this industry was no more. It almost completely vanished in a single generation, displaced by ammonia compressors. And it was precisely at the moment of its disappearance that the historical memory and understanding of how complex it was also faded away. There is a term called technological amnesia. This is when a new technology replaces the old one so quickly and completely that in 20 years, no one remembers how the previous system worked. And 100 years later, it is described in 2 words: kept ice in cellars, as if nothing more complex than a pit with straw ever existed. 8,000 enterprises, tens of thousands of professionals, transcontinental logistics, international trade, specialized architecture across 3 continents, 500,000 tons per year from one company. Is this kept ice in the cellars? This is what happens to the history of technology when the new replaces the old too quickly. The electric compressor wins, and everything that came before it falls into the category of imperfect predecessors. A few amusing facts, a few curious details, nothing systematic, nothing that makes you ponder how thought out, extensive, and globally interconnected it truly was. But wait, let's approach it from a different angle. In 1915, almost 25 million tons of natural ice were produced in the United States. 25 million. By 1930, this industry had shrunk to just a few million tons. By 1950, it had virtually disappeared. 35 years. A whole global industry evaporated in 35 years. It's very fast. And this speed is one of the main mechanisms of technological amnesia. If the transition had taken 200 years, like the shift from wooden ships to steel ones, history would have been preserved in detail. Each generation would have had time to pass it on to the next. But 35 years is just one human life. The people who worked as ice cutters in 1915 lived until 1950. They witnessed the disappearance of their profession during their lifetime. And their children no longer needed to know that. Technological amnesia works precisely like that. Not through prohibition, not through the destruction of archives, simply through changing generations and the loss of practical relevance. And now the final question I propose you hold in your mind. When electricity is cut off in the world today, after a hurricane, after a technological disaster, after a military conflict, the first thing to stop working is the cold chain. Food, medications, blood in blood banks. All of this relies on uninterrupted power supply. The Persian icehouse would continue to function in this situation. The Norwegian mountain lake would freeze every winter. Gravity hasn't gone anywhere. We have created a system that is more powerful, efficient, and user-friendly than anything that came before. It's true. But in doing so, we've forgotten how another system worked. The one that didn't require an outlet. And here's what's strange. Between the icehouse and the electric refrigerator, 23 centuries of continuous engineering development in the field of cold management. 23 centuries. And in the popular accounts of the history of technology, this period seems to be non-existent. There is a leap straight from people stored ice in cellars to, in 1913, the refrigerator was invented. Ask yourself one question. If 500,000 tons of ice per year is a primitive technology, then why is there not a single page in textbooks about the infrastructure that made this possible? Where are the maps of Swift's ice refueling stations? Where are the diagrams of Gotti's wells? Where are the calculations of the insulating properties of the sarouge? They are gone. Not because they never existed, but because when the electric compressor emerged, this infrastructure was no longer described as a cohesive whole. It broke down into individual curiosities and dissolved into footnotes. The mechanical refrigerator did not invent the management of cold. It replaced it. And the difference between these two words is fundamental. Because the old system was architectural. It relied on the mass of the building, the shape of the dome, the depth of the basement, and the proper choice of location in the terrain. It utilized the physics of climate as building material. The new system has become energetic. It relies on the power grid, on the uninterrupted supply of refrigerant, on the factory that produces compressors. The first system could last 1,000 years without a single repair, as long as there is winter and a night sky. The second one shuts down a few hours after the power goes out. And we call this progress. Perhaps it is, but then we must honestly acknowledge it was not just a technological replacement. It was a shift in the type of dependency, from topography and architecture to energy networks and the entire infrastructure that supports it. The Yakhchal in the Iranian desert has stood for over 2,000 years. Some of them operated even in the 20th century, not because there was nothing to replace them, but because electricity arrived in that region later than the need for natural ice disappeared. Engineers studying zero-energy buildings today are turning back to the design of Yakhchals, not as a museum exhibit, but as a working model, because the shape of the cone the angle of the shading wall, the depth of the underground chamber. These are not folk art. They are engineering solutions that function regardless of the price of electricity. And apparently, they were discovered and optimized thousands of years before anyone explained the physics on which they rely. Herein lies the paradox. We think of ourselves as the pinnacle of technological advancement. Yet we are rediscovering principles that were realized in clay and egg whites 2,400 years ago. It speaks of something. And now a question that I will leave unanswered. We have examined 4 systems: Persian, American, British, and again American. This is the Western and Atlantic branch of one global story. But at the same time, Japan was constructing state ice chambers and building temples to the god of ice. China was developing portable bronze refrigerators 2 millennia before General Electric. Spain maintained a network of 28 snow wells in the mountains as a municipal medical service. Sicily exported ice from Mount Etna to the Knights of Malta for military hospitals. Peter the Great established state authorities to manage the cold chain on the Volga. This is another story. A story about how cold was transformed not into a commodity, but into a state resource, into an instrument of empires, into an object of religious worship, into a strategic asset that determined who would survive a siege and who would triumph in war. But that's a separate conversation.